Proxima Centauri b, the closest exoplanet to our solar system and a celestial neighbor that has long intrigued astronomers, has recently become the subject of renewed attention and speculation. Detected mysterious bright flashes. Could this be a sign of an alien civilization? Stay tuned for more. For a long time, scientists and ordinary people alike have been eager to imagine what life beyond our planet might be like. The possibility of alien life has captivated imaginations and inspired generations. Any science suggesting the existence of something beyond Earth has always been greeted with enthusiasm, wonder, and a renewed sense of purpose in the search for cosmic companionship. Then came a turning point, one that electrified the scientific community, when the James Webb Space Telescope delivered clear indications of life somewhere in the cosmos. While scanning the depths of space, this powerful telescope detected something absolutely fascinating on Proxima Centauri b, a distant exoplanet orbiting the red dwarf star Proxima Centauri. What it observed were lights that bore an uncanny resemblance to those of terrestrial cities, lights that flickered in patterns too organized to be dismissed as mere natural phenomena. These unusual observations raised a profound and thrilling possibility that an extraterrestrial city might exist on that distant planet. The idea generated great excitement and intense curiosity among scientists and researchers around the world. They are intrigued not just by the potential for life but by what kind of intelligent beings might be organizing their societies in ways that we are just beginning to discover. Could these beings be using technology similar to or more advanced than our own? Could they be reaching out in ways we have yet to comprehend? Looking at these distant city-like lights, which are located an incredible 4 light-years away from Earth, NASA engineers and astronomers alike are amazed. They wonder, how long have these lights been visible in space? How long have they been waiting for our technology to evolve enough to detect them? David Kipping, an astronomer at Columbia University, described the planet where these lights were found as particularly complex. This complexity is due to the fact that, unlike most rocky planets which absorb sunlight and emit energy in the form of infrared radiation, this exoplanet appears to behave differently. Its behavior is shaped by its unique relationship with its parent star, Proxima Centauri, a small but highly active red dwarf star. This particular discovery, made possible by the extraordinary capabilities of the James Webb Space Telescope, underscores the importance of continued astronomical exploration. The telescope's ability to capture infrared wavelengths played a critical role in detecting the unusual behavior of Proxima Centauri b. This function is crucial in understanding the atmospheric conditions of this nearby exoplanet. Researchers now plan to continue using the telescope to explore the planet's atmosphere in greater depth. One of the primary objectives is to investigate whether the planet might be habitable. The James Webb Space Telescope is especially sensitive to infrared light, which allows it to observe phenomena on Proxima Centauri b even during its nighttime phase. For many telescopes, it is incredibly difficult to detect faint light in the vast darkness of space, especially light that may be artificial in nature. However, the James Webb Space Telescope is capable of picking up even the faintest glimmers of light, which makes it an ideal tool for confirming whether the supposed city lights observed on the dark side of Proxima Centauri b are real and not some form of natural interference. The telescope can detect artificial light in space if it falls within a very narrow frequency band, much narrower than the light typically emitted by stars. This ability to discern highly specific wavelengths allows researchers to isolate potential signals from exoplanets like Proxima Centauri b. This planet, in particular, has a dynamic and evolving relationship with its star. One of the planet's fascinating characteristics is its potential to enter a tidal lock, where one side always faces its star, and the other remains in perpetual darkness. Numerous solar planets capture their star's intense energy in similar ways, and their reflected spectrum varies depending on atmospheric and surface conditions. As Proxima Centauri b revolves around its star, it experiences a day and night cycle that is somewhat similar to Earth's but with some notable distinctions. It endures intense heat during its daytime phase and significantly cooler temperatures at night. These temperature swings are mainly influenced by the planet's composition. For example, if Proxima Centauri b lacks an atmosphere, the temperature difference between day and night would be extremely dramatic. Without the moderating effect of atmospheric gases or bodies of water like oceans, the day side would warm significantly, possibly to uninhabitable levels, while the night side would plummet to sub-zero temperatures, making it a frozen, hostile environment. This dramatic thermal variation is an area of great interest to astronomers, as it offers crucial clues to the atmospheric compositions and geological conditions of Proxima Centauri b. The James Webb Space Telescope, with its advanced ability to image in the infrared spectrum, can effectively analyze the planet's thermal emissions. These observations provide valuable information about its atmospheric properties, such as whether the planet has a protective ozone layer, cloud coverage, or greenhouse gases. Interestingly, the James Webb Space Telescope's orbit around the Earth coincides with the orbital period of Proxima Centauri b, allowing detailed observations of its daylight and nighttime cycles to be made approximately every 11.2 Earth days. If the planet indeed has an atmosphere, the next logical step for scientists would be to examine its chemical composition in greater detail. This would involve scanning for life-supporting elements such as oxygen, water vapor, and methane, all of which would be indicative of habitable conditions. If these elements are detected on a planet, it would serve as a strong confirmation of its potential to support life. This endeavor would require analyzing the light that passes through the planet's atmosphere, a complex and technically challenging task. Although the James Webb Space Telescope excels in characterizing planetary atmospheres, it's primarily designed for broader astronomical functions such as studying the early universe and star formation. Nevertheless, it is quite adept at analyzing variations in the concentrations of critical elements like water vapor, carbon dioxide, and methane. Despite its limitations in detecting free oxygen, a key biosignature, the telescope is capable of searching for other essential elements such as ozone. The presence of ozone, for example, would suggest a planet has a stable and potentially life-sustaining atmosphere. As scientists continue to examine the immense volumes of data from the James Webb Space Telescope, the search for distant worlds continues. Each new finding brings us closer and closer to answering one of humanity's most profound questions: are we truly alone in the universe? Essential to remember, however, that the James Webb Space Telescope can observe only a limited number of exoplanets, particularly those closest to Earth. For more detailed atmospheric studies and to probe deeper into the mysteries of far-off planets, astronomers will turn to ground-based observatories such as the Extremely Large Telescope, ELT, which is scheduled to begin operations in 2028. The ELT is designed to offer a more detailed look at the atmospheric structures of distant exoplanets. It will provide clearer and more comprehensive data on their potential to harbor life by studying their surface temperatures, atmospheric pressures, and chemical makeup. Scientists are eagerly looking forward to the operation of future space telescopes like the ELT. In the meantime, the James Webb Space Telescope remains an indispensable tool in the exploration of distant exoplanets. Despite its limitations, it continues to provide valuable information that could fundamentally transform our understanding of what lies beyond our solar system, both now and in the decades to come. Researchers have ambitious plans for the next generation of space telescopes. They want to develop advanced technologies that can effectively reduce or block starlight to better observe the faint light reflected by the planets orbiting those stars. It is akin to using your hand to shield your eyes from the sun to get a clearer view of what lies beyond the glare. By dimming starlight, these future telescopes will be able to study the faint light reflected by exoplanets more clearly. This will allow astronomers to analyze their atmospheres and determine whether they may harbor life. However, this task remains a considerable challenge. Blocking out starlight to observe exoplanets is easier said than done. Stars are incredibly bright, often outshining their surrounding planets by orders of magnitude. This makes it extremely difficult to detect the faint light that planets reflect, which is essential for studying their characteristics and determining their potential for habitability. To tackle this monumental problem, scientists are developing several innovative techniques. One such method is the use of coronagraphs. These are specialized optical devices placed inside telescopes, designed specifically to block out starlight while allowing the light from orbiting planets to pass through. By carefully shaping and filtering the light waves, coronagraphs can significantly reduce the glare from stars, making it easier to detect the dim and elusive light from exoplanets. Another highly promising technology is the Starshade, a giant, flower-shaped spacecraft that flies in perfect formation with a telescope positioned tens of thousands of kilometers away. The Starshade effectively blocks starlight before it even enters the telescope's optics, allowing only the light from the exoplanets to reach the scientific instruments on board. This method could be especially